All right, howdy. So this is part 3, the last part of the lecture. What I'm going to talk about here is the law of inertia, or I'm going to talk about more or less what happens for the part of the law of inertia where something's moving. So we originally started with the translational stability, right? Something that doesn't let something move, right? We talked about rotational stability. You put those together and you end up with this kind of stability that you need to build a building or a bridge or something like that. Here we're going to talk about the second part of that first thing we talked about, which is what happens if the same condition, an object feeling a balanced force, or the forces on an object balancing, what happens then? Okay, so what we're going to say then is that an object that moves in a straight line at a constant speed so he's moving in a straight line. For some reason, I think you'll find out this out later. That my writing was better backwards on a piece of plexiglass than this. So got something just doing this. He's here. He's moving at a constant speed. We'll call speeds v for velocity. So he's going straight in this direction, and an object moving in will continue to do so unless disturbed. That is, unless there's a net force on it. So if we have a straight line like this, straight line, constant speed, that just means that the object has no net force on it. If we see that rather than this, there's a point and it starts moving like this, that means right here there was a force, or actually a net force, that didn't balance out. So all of a sudden, the thing moves in a different direction. Next time we'll talk about what to do in that case, right? Or how to analyze this, at least a little bit, to talk about how the velocity changes. Right now, all we care about is if the velocity changes. If either the speed changes or the direction changes, then something has to be doing that, right? You're disturbing the motion of the object. An object will go in a straight line forever unless something's disturbing it. Now, this is, where people had such difficulty for at least 2,000 years in putting all of this physics stuff together, is that most terrestrial things, most aquatic things, if you stop pushing them, they stop going, right? And that's because they're always in contact with all sorts of other things. So a boat, for example, is always in contact with the water. So I can also write this another way. When the forces balance on a moving object, its speed and course are constant. I don't have any room, do I? No, that's a marking. Okay? So you just keep on going in a straight line. Like this sailboat, right? So if you have a sailboat, let's say you've got a tailwind. The tailwind pushes it forward, right? That's why you like a tailwind. And the water here has drag. So you have water resistance from the hull. When these two things are equal, then the boat moves at a constant speed. Okay, so this is going to be true for a propeller as well. It doesn't matter what it is. If you have a propeller and the drag, the water resistance, they're going to cancel out if you're moving at a constant speed. If you're if you have the constant speed, they're the same. If you want to speed up or slow down, you have to increase the power to your propeller, right? You have to increase the speed the propeller is turning. That provides more force, and then you can speed up. What happens with water resistance is that it gets greater as the faster you go, which you may notice if you try to move fast in underwater, so that you'll always get to a point where you get a constant speed. And we'll talk about this a lot when we're talking about water resistance and air resistance in the second unit. So that's all that happens. That's all the difference is for the law of inertia for a moving object. Okay, so I'll do an example for this, and then we'll be ready to get to part two. All right, bye now.